welcome back. In today's session, let us look at the concept of transistor biasing. Okay, so first let us try to understand the process of biasing. What do you mean by biasing? So in simple terms, biasing means establishing required transistor voltages and currents with the help of external DC power supply and resistor. So using biasing, you will be able to establish required transistor operating conditions. Operating conditions as in voltage and current. Okay, using some resistors and power supply. Using biasing, basically we establish the required voltages and currents. Okay, what we can achieve using biasing? So using biasing, one can make a transistor to talk as in you can make a transistor to work as an amplifier, or you can operate a particular transistor as a switch. Okay, what do you mean by switching operation? So in case of PN junction diode, we had seen that whenever you forward bias a diode, it acts like a closed switch. On the other hand, when you reverse bias a particular PN junction diode, then it acts like an open switch. So similarly, a transistor can be operated either in switching mode or in amplifier mode. Okay, so that is possible using biasing. So using biasing, you can make a transistor to operate as a switch or an amplifier. Or an amplifier. So instead of using a mechanical switch is your conventional, single pole switch on off, right? So instead of mechanical switch, you can also think of realizing an electronic switch, and for that you can use a transistor. Okay, so you can perform on bar off operation. So that is one of the major application of transistor. Okay, and in case of amplifier, what we do is, let's say you have a low amplitude input signal. Okay, let's say for example you have a microphone. Okay, so in the microphone, what do? We utter the voice templates, right? So when we speak, so the microphone basically it acts like a transducer, right? So mechanical vibrations are then converted into electrical signal. So this is your mechanical vibration. So voice is considered as some waves. So basically it will be picked by this transducer microphone, and it will convert the mechanical vibration into electrical signal. So input is the voice templates, and the output going to be electrical signal. So the problem is that the microphone gives out the electrical signal in the range of a very small amplitude. So in the range of millivolts it gives out, right? And with this amplitude, you will not be able to drive a loudspeaker, because speakers usually operate at a larger power level. So you have to enhance, in the sense you have to increase the power level of the signal. So for that, you can use a power amplifier, or you can also use an audio amplifier. So audio amplifier increases the voltage level of a weak incoming input signal, and on the other hand, power amplifier amplifies the power level so that whatever the signal which is coming out of the microphone, that can be easily fed to a loudspeaker. Loudspeaker is nothing but the music system what you use at your home. Okay, so for that we use an amplifier. So it gives out large signal output. So this is the typical example of a biasing circuit. So you can either make the transistor to work as a switch, or you can make the transistor to work as an amplifier. Okay, so switching application, as I mentioned, you can use it as an electronic switch, for on-off applications, and amplifier you can use whenever you are in a need of amplifying weak input signal. So that being said, now let us try to understand the concept of operating point. So this operating point is nothing but it is consisting of the details of voltage and current. Two-dimensional plot, voltage and current. Okay. Now, in order to explain the operating point, let us try to consider a particular transistor configuration. So, in this module, we are going to concentrate only on BJT, which is a bipolar junction transistor. So, in BJT, there are two types, NPN and PNP. So, analog electronic circuits is a third semester course, and about BJT operation, that is NPN BJT operation and PNP BJT operation, you have already studied in basic electronics. Basic electronics. So I expect that you have good understanding of the transistor operation. So this is the prerequisite. You must know the operation of transistor. Okay, in NPN type as well as in PNP type. All right. So generally we consider NPN transistor because mobility of electrons is greater than the mobility of holes. So that's why we generally consider NPN transistor. You can also realize any given amplifier circuit or a switching circuit using PNP transistor as well. Just that you have to reverse the voltage levels and current direction. Okay. All right. So let us consider an NPN transistor. So this is the symbol of NPN transistor. Okay. This is the collector terminal, base terminal, and the emitter terminal. This is NPN type. Okay. Side by side, let me also draw the device symbol of PNP transistor. The three terminals, collector, base, and emitter. So in case of PNP, this arrow direction is inward. NPN arrow direction is outward, and in case of PNP the arrow direction is inward. Okay. And you can mark various transistor currents, right? So let me use a different color. So this is collector current, this is the direction of base current, and in the direction of arrow you have to mark the emitter current. This is emitter current. Alright, in case of PNP transistor, as I mentioned, you have to interchange the current direction. Okay. How do we do that? So over here, your emitter current is in the outward direction, right? And in case of PNP, it is in the inward direction. Okay. So you have to flip the direction of base current, and you need to flip the direction of collector current as well in case of PNP transistor. Okay. The aim is to satisfy this current equation of the transistor. That emitter current, IE, is basically equals to base current plus collector current. So whether it is an NPN transistor or whether it is a PNP transistor, so PNP, you always see that the transistor current equation is unaffected, right? So summation of IC and IB gives IE for NPN, and likewise summation of IB and IC gives emitter current IB. Okay. So only the current direction changes, but the equation remains the same. So that's what I was trying to tell you in the beginning. So if at all you have to realize a particular circuit using a PNP transistor, all you have to do is change the current direction and also change the polarity of voltage. Okay. So that is about the currents. Okay. Now let us talk about the terminal voltages. Okay. in transistor, you are supposed to mark the terminal voltages as well. Okay. So between base and emitter, whatever voltage you trace, that is called as the first terminal voltage. So potential difference, right? So you are measuring the potential difference between base and emitter, assuming that base is at higher potential and emitter is at lower potential. All right. On the other hand, if you measure the potential between collector and emitter terminal, the resultant potential can be considered as VC, assuming emitter is at lower potential and collector is at higher potential. Okay, and the third terminal voltage going to be VC. Okay, assuming base is at higher potential and collector is at lower potential. So this double subscript notation, I guess you are aware of it, right? Suppose say if we mention something like determine the potential difference Vxy, it is assumed that X is at higher potential and Y is at lower potential. You may end up in getting plus voltage or minus voltage. That is okay, right? So this is just assumption that base is operating at a higher potential compared to emitter. Okay, and in case of transistor, so this VB, okay, so this VB is equals to the threshold voltage of the semiconductor material. Okay, for example, if your transistor is constructed using silicon material, then the barrier potential of the PN junction for a silicon diode going to be 0.7 volt. So this is for silicon. On the other hand, if you construct a transistor using germanium material, the barrier voltage going to be 0.3 volt. Okay. Now, silicon is a widely used semiconductor material, and germanium material is seldomly used due to the several advantages offered by silicon material. The first advantage is the availability. Silicon is available in abundance, okay, and the manufacturing cost to extract silicon is comparatively less compared to germanium, right? So that being the first advantage. The second advantage is that silicon has excellent temperature withstand capacity. So a silicon material can handle higher temperature levels than germanium, and that's why the cooling requirement the cooling requirement is not so important factor when it comes to silicon material. On the other hand, germanium is prone to thermal runaway due to the temperature problems, and you need an excellent cooling mechanism for germanium transistors. So, and that's why you see that normally the silicon transistors are widely used. Okay. All right. And similarly, you can mark the terminal potentials for a PNP transistor as well. Okay, the only difference is that you have to interchange the polarities. Okay, so for example, for one potential I'll write, so over here base will be at lower potential and emitter will be at higher potential. Just you have to reverse the polarities of voltages and reverse the current directions. Alright. So this is about the various transistor currents and voltages. So now let me get into the concept of operating point. Now to explain operating point, which is generally represented as Q point. Operating point is popularly called as, and Q stands for quiescent point or operating point. Q point or operating point is one and the same. Alright. For this, let us consider common emitter configuration. So in the introductory course, that is basic electronics, you must have studied about the different transistor configurations, right? The different transistor configurations are common emitter, common base, and common collector. So let me write common emitter, common base, and common collector. Okay, and they have certain differences between them. For example, if you consider common emitter offers 180-degree phase shift. On the other hand, common base offers 0-degree phase shift, and common emitter gives current gain in the range of hundreds, and in case of common base, the current gain is approximately equals to 1. So these are the different features of each and every configuration. Okay, out of the three configuration, we are concentrating on common emitter configuration, because common emitter configuration is widely used in amplifier purpose as well as for switching purpose. So keeping that in mind, we are going to spend more time on common emitter configuration and common base configuration. Let us solve one or two problems based on common base configuration. Okay, common collector is seldomly used, and that's why not much emphasis is given. All right, so fine. So common emitter configuration, let us consider. So as the name suggests, okay, emitter terminal is common. So common emitter means emitter terminal is common. So what you have to do is you have to draw the transistor symbol, and for the explanation purpose, I consider NPN transistor. So emitter circuit is made common to input circuit as well as output circuit. So this is how you can visualize. So this is your extended emitter terminal, right? E as well as E over U. All right. So let us try to mark the transistor currents and voltages. So this is your base current, and this is your collector current, and this is your emitter current. And also let us mark the voltages as well. This is your input voltage, VB, assuming base is at higher potential compared to emitter, and this is the output voltage, VCA. Okay, we'll not worry about what is the voltage that exists between base and collector terminal. Okay, that can be found simply by finding base to ground voltage and collector to ground voltage. Okay, we'll talk about it sometime later when we solve actual problems in biasing. All right. This side is considered as the input side. So this is your input circuit, and the right hand side is considered as your output circuit. Okay, so that's why in future classes, instead of saying apply KVL in the input circuit, I may say that apply KVL in the base emitter loop. So if you look at the input circuit, in the input circuit, you can observe two terminals, right? Base and emitter. So your input circuit is comprising of BE loop. What is BE loop? Base emitter loop. On the other hand, if you look at the output side is nothing but the right hand side. You can identify two terminals, at the output side. Those two terminals are collector and emitter. Hence, the output circuit can also be considered as CE loop. So CE loop as in collector emitter loop. So input circuit is base emitter loop and output circuit is collector emitter loop. Okay. So base emitter loop, if you look at base emitter loop, you would find the input voltage, right? VB. So your input V in can be considered as VB, and VC, since it is observed at the output side, you can consider it as V naught or V out. Okay. Similarly, the current which is found on the input side is called as the input current. So whatever input current IB you are seeing, that can be considered as II. And on the other hand, the current which you are seeing on the output side can be considered as I naught. Okay. So once you identify the input output voltages and input output currents, you'll be able to comment on something known as the gain. Okay. Over here, let us concentrate on DC gain, okay, which is the DC current gain. For common emitter configuration, the current gain, which is nothing but the ratio of output current to input current, is considered as beta. And what is beta? Beta is equal to I naught by II. So the definition remains the same, whether it is common emitter, common base, or common collector. So current gain of any configuration is found using this formula, I naught by II. On the other hand, this beta letter, Greek letter what we have used, that is configuration specific. For common emitter, the current gain is denoted by beta. On the other hand, if at all you talk about common base, the current gain is denoted by alpha, and for common collector, the current gain is denoted by gamma. And for common emitter, as I mentioned, it is beta. Okay? All right. So with respect to, this context, the current gain beta going to be I naught by II. And what is II? Sorry, I naught? I naught is collector current. And what is your input current? Input current is IB. All right. Okay. Beta is equal to, and what is the order of collector current? Collector current is in the order of few milliamperes, right? On the other hand, what is the order of or the range of base current? Base current is in the range of micros of amperes. Okay. So a typical ratio of milli by micro will give you beta in the range of few hundreds. Okay. Typical range is say some 100 to 200 or even 75 to 150, something like that. So in few hundreds, the typical beta range, you are going to get it. All right. And any reason why base current is in microamperes, why it is so less? You have to again roll back to the transistor operation. So base layer is a high purity layer. Okay, when you have a high purity layer, obviously the resistance is quite large, right? So conductivity is poor. Since the base layer is a very pure layer, okay, that's why the charge carriers are less in that particular layer, and that's why the current which flows in base layer is in the range of micros of amperes. On the other hand, if you look at the collector layer as well as emitter layer, so they are made up of N type of material, and you have good amount of doping present in collector and emitter layer, and that's why the conductivity is pretty good compared to base layer, and that's why you get appreciable amount of current flow, and that's why collector current and emitter current are comparatively very high in comparison with the base current. Okay, so this is for common emitter configuration. Okay, if you look at common base, okay, in case of common base, this is how you can draw the circuit. Okay, so the base layer should be made common. This is collector, this is base, and this is emitter, right? So this is your IE, IB, IC. So IB plus IC gives IE. Okay, so IC is I naught here and IE is II here, and that's why the current gain, which is termed as alpha. So current gain is nothing but I naught by II. So output current to the input current. So what's your output current? Output current is IC. And what is your input current? Input current is II, which is nothing but IE. Okay, or you can write IC divided by IE. So what is the transistor current equation? IE is nothing but IC plus IB. Since IB is very, very small in comparison with IC, so alpha can be approximately written as IC by IB, and it is very close to 1. Okay, alpha is very close to 1. Okay, example, alpha is normally in the range of 0.98 to 0.99. It is always slightly less than infinity because denominator is slightly greater than numerator, because denominator is IC plus IB and numerator is only IC. So that's the current gain for common base configuration. On the other hand, if you look at common collector configuration, the collector terminal is common. The collector terminal is common for both input circuit and output circuit. So yeah, we can mark the currents. This is IB and this is IC. So the current gain, which is the ratio of I naught by II, okay, is considered as gamma, and gamma is equal to I naught. So what is I naught? I naught is IE, right? And what is II? II is the base current IB, right? So as you know that in a PJT, the operating level of emitter current is in the range of few milliamperes, and the base current is typically in the range of microamperes. So that's why the ratio IE by IB gives a pretty high current gain, just like your common emitter configuration. The only difference is that in case of common emitter, you have had IC in the numerator. On the other hand, in case of common collector, in place of IC, what do you have? You have IE, and IE and IC are approximately equals to each other, and that's why just like your beta, you get pretty high gamma as well, right? So gamma is pretty high. It is in the range of few hundreds. Remember, it is unitless, okay, because current by current gives dimensionless quantity. All right, so now that we have seen the 3 different configurations, we can actually look into the operating point. So the operating point is basically found in the transistor output characteristics. So to talk about operating point, we should have the transistor output characteristics. Okay. So first let me draw typical transistor output characteristics. Okay, the transistor output characteristics can be obtained from the data sheet. Okay, so it is mentioned in the data sheet. So for this, we will consider common emitter configuration.